Hello and welcome back to the lecture on applied econometrics. So in this lecture we are going to talk about
autocorrelation. Now, autocorrelation is a problem when we have our regression model. It may, if the autocorrelation is present, then we need to actually address that, like we have seen in the previous cases, heteroscedasticity, multicollinearity. If those issues are present in our regression model, then we need to actually do the diagnostics and actually, find a way out to sort of get rid of those errors or those problems. Similarly, if autocorrelation is present in our model, so we sort of need to find a way to actually get rid of the autocorrelation. Now, what is autocorrelation in the first place? Now, we know from the Gauss Markov assumptions, if we need to have sort of the best, if we need to have the sort of best linear unbiased estimator for the regression equation, so what we need to have is that we need to kind of fulfill few criteria, and for that we need to have one criteria fulfilled, that is covariance among the error terms. Let's say I will write I and uj, let's I and j be two different observation, has to be 0. So essentially it means that the error term related to observation I and the error term related to observation j are uncorrelated. There is no correlation. Now, particularly for autocorrelation, we use the term t instead of I and j. So how we actually write that? We write it as covariance of ut and ut prime, let's say, is equal to 0. So that is what we have to have if autocorrelation is 0. If autocorrelation is 0. Now, why we have these different notations? Well, uh, essentially, autocorrelation is something that we will see in time series data. Mostly it is related to time. So the very term auto is from the Greek word, and auto means self. Auto means self, okay? So basically I'm correlated with myself, okay? So if I need to be correlated with myself, the data generating process would require me to have some sort of time dimension. So that is why autocorrelation is a problem that is mainly seen in case of time series data. For example, if you take, let's say, GDP, you will find, if you will actually need to look for if the GDP of one period is related to the previous period, which usually is the case. And let's say if you look at temperature data, for example, which we are going to see in this talk, so you will need to actually see if the temperature data of this period is actually correlated with the previous period. All right. So essentially, autocorrelation. Now you have learned previously heteroscedasticity, and we know for heteroscedasticity, the formula is something like this. Autocorrelation and heteroscedasticity is pretty close, but in case of autocorrelation, we have the connotation of self is involved. Okay, heteroscedasticity, you can have two different variables, but in case of autocorrelation, it is only with the self, and the time dimension is important in case of autocorrelation. All right. Now, if we want to actually see further what happens because of autocorrelation or why autocorrelation is present, so let's first talk about why autocorrelation is present. Autocorrelation usually it happens because of some omitted variable. Okay, let me explain that. So let's say y is actually determined by some x1 and x2, but there is another omitted variable xov, let's say. Okay, now when I have, and that is actually out of my model, now when I have y at time period yt, now the xov will have a value of xovt, let's say. Now this xovt is actually out of this model, it is not included, right? Now yt prime, when I measure yt in yt prime time, so I have my yt prime, and then there is an xov t prime, right? Now because you are omitting this xovt and xovt prime, so whatever pattern is there in xovt or xovt prime, ovt prime, so then that part will be reflected in the error term. Okay, so the ut and ut prime will actually capture this xovt, and xovt prime will contribute to ut and ut prime. Okay, and that is the reason, because the ut and ut prime is capturing this xovt and xovt prime, it will actually show that there is some pattern in the xt, ut and ut prime. Now, going by this, we can actually see that autocorrelation mostly are of two types of autocorrelation. If we look at mostly of two type, first it is a positive autocorrelation, and let me explain what I mean by positive autocorrelation. Positive autocorrelation. So in case of positive autocorrelation, we will essentially the this value, let me use a different color, this covariance ut and ut prime, they will lead to a value which is greater than 0, let's say, not equal to, greater than 0. Okay, so if it has to be greater than 0, so in at what condition we will have the covariance between two variables is actually greater than 0? So if they both have a positive, the same sign, right? Either they both are positive or both are negative. So what I mean by they both are positive and they both are negative, so to illustrate that, let me actually draw this. So let me actually draw, let's say, this is my independent variable in the along the x-axis and my dependent variable along the y-axis. So let's say this is my x and this is my y. Let's say this is only x is what is determining the y. And then I have my regression line. Let me draw my regression line with a different color. Okay. And then let's say we have our error terms. All right. Let me actually plot these errors. So let's say these are my error terms. And you can see that I'm actually plotting something. Perhaps there is a pattern, and of course there has to be if I actually want to illustrate the autocorrelation. So let's say we have something like this and this and this and this and this and this. So essentially, if I take ut and ut, so let's say if we take this error terms in successive period, let's say this is ut and this is my ut plus, or I should not write it here, it is x-axis. Let's say this is ut, this is ut plus 1, this is ut plus 2, this is ut plus 3, and so forth. Okay, so essentially if I take correlation between ut and ut prime, ut plus 1, so then I will have a positive value, right? Because they both are positive. Similarly, ut plus 1 and ut plus 2, they're positive. They're above the regression line. Both the errors are bearing the same symbol. They're both positive. But when I change the direction, when I move from positive to negative, then I will have my correlation coefficient that will bear a negative sign because their terms are of opposite sign. But then here again, if I just repeat the same exercise all throughout these lines, so I will have all these values are going to be positive because they're on the same side of the regression line. So both are both the error terms are negative. So when two negative terms I take correlation coefficient, they're going to basically give me a positive term, right? Similarly, on the other side, all positive error terms, and they're going to give me a positive correlation coefficient. And this is precisely why we call this correlation, autocorrelation to be positive autocorrelation, because whenever I take the error terms, the correlation coefficient of the error terms, as long as they're on the same side of the line, we are going to get a positive value, right? So it doesn't matter if my line is on the positive side or the negative side. All I care is if two successive values are bearing the same sign, right? So that is, so in this kind of examples, the autocorrelation we see is a positive autocorrelation. Of course, we have autocorrelation because we can see the residual term that we have that actually is bearing a pattern, right? So that is actually showing some sort of sinusoidal pattern, right? So it is going up and coming down and going up and so forth, right? So there is a pattern. So that means they're related to each other, and the relation essentially, as we understood now, is a positive autocorrelation. Okay, mostly we'll see in problems in economics, we'll mostly see positive autocorrelation and not much of negative autocorrelation, and I'll explain why is that. But before that, I need to explain what I mean by negative autocorrelation. Just one more point to note: this amplitude and the cycle of this positive autocorrelation, that is absolutely dependent on data. So we really don't have, that's random. We really cannot say anything. But we can say about positive autocorrelation that's a slow process. So every error term is actually correlated with the previous term, and they had same sign. So essentially, it has to be a slow process. It cannot be very abrupt. It cannot go up and down, right? It cannot go up and down. It cannot do that. So that's the positive autocorrelation part. So now let us talk about negative autocorrelation, the other type of autocorrelation that we're talking about, negative autocorrelation. Negative autocorrelation. And what is negative autocorrelation? I hope we are maintaining the same color consistency. Let me just check. Positive, yeah. So in case of negative autocorrelation, we will have covariance ut, and ut plus 1, ut minus 1, it doesn't matter, is actually less than 0. So when that is possible, covariance ut and covariance ut plus 1 is less than 0. That is possible if we have something like this. Let's say we have the same regression line, but the points, they need to be on the two sides of this line, so that whenever I take the successive points or the successive error terms, they actually have different signs. So that's all I care, whether the successive observations are, and the error terms basically are of different signs. So if I draw this, it is going to be something like this. It's going to be something like this. Go up, go down, and again up and down and up. So essentially, I can see that the error term ut here, let me use a different color. The ut here, oops, I have deleted some of the lines I just drew. So ut here, ut and ut plus 1 and ut plus 2, they are on the opposite side of the regression line. So one is positive and the next is negative. Again, the next one is positive and next one is negative, and so forth. So as long as they're on the different sides of the regression line, this condition is going to be satisfied, right? Now that is what is called negative autocorrelation, because of the value of the covariance among these two error terms, right? Now that essentially means the process has to be highly sort of fluctuating. So if the stock is going up in this period, it's going to go down tomorrow, and again day after tomorrow it is going to go up. So it has to be really very sort of extremely fluctuating process. And in economics, usually we don't have this kind of data. We can have, but not usually. Mostly, I mean, in case you find negative autocorrelation, it is very important that we check for modular specification or functional specification, because the very formula we write, that might have a component that will sort of represent the model, like it has it looks, the error terms are looking like this zigzag pattern, right? So check for modular specification or functional specification, model or functional specification, if we have such kind of negative autocorrelation. All right, so this is about the introduction to autocorrelation, and in the next lecture we are going to give an example of autocorrelation. Thank you.